Okay, so we are looking at polynomials from a graphical perspective. Just to clarify some vocabulary from IM3. If we look at a polynomial like the one given here, this is a polynomial in n form. It's an nth degree polynomial. The ellipsis here is used to indicate that there are possible expansions or retractions. So it's one way of defining every polynomial, whether it's linear, quadratic, cubic, or higher order. They're all defined by this particular format. The lead coefficient. So the leading term, the leading term is this one. The leading term is always the polynomial, the term with the highest degree. Even if they're not written in the correct order, you have to rearrange the order. The leading term is going to be a n x to the n. The degree of this polynomial, therefore, is going to be nth degree, and our lead coefficient is a n. Just clarifying some vocabulary we'll have learned last year and the year before. So in our first example, finding the leading coefficient and the degree of the following polynomial. So the lead coefficient in A is going to be 3, and the degree is going to be 4. So in B, who can help me here with the degree? Let's start with the degree, maybe. Check at the front, please.
Oh, with the degree, it's 4.
No.
Oh, no.
This one is 3. This one is going to be third degree.
And 7.
Why is it third degree?
Because of the power of 3.
It's the highest exponent.
It's the highest exponent. The highest exponent. What will the leading coefficient be? This lady here? Excellent. -7. G. Right. Who's going to tell me what the degree of this one is? Lady in the corner? This is a 0th degree. What is the leading coefficient? 4. Good guess. There's not really any other numbers there. Yeah, must be 4.
Sir?
Yeah.
Wouldn't the degree be 1 if it was 4 to the power?
No, that would be linear.
Oh, okay. But if it was 4 to the power 0, wouldn't it be 1? Oh, okay.
Exactly.
Okay, thank you, sir.
Okay, so we are looking at the concept of extrema. So an extreme point is where the graph reaches at one particular interval its greatest value. A polynomial can have a relative or a relative extrema. This can either be a relative maximum or a relative minimum. What it means by relative is that it is relative to one particular section of the curve. So here in this particular curve, we have a relative extrema. We can see that the local minimums are going to be here and here. We have 2 possible local minimums. The local minimums occur at x equals -4 and x equals 0. The local maximums are going to be here and here. So this is x equal to -2 and x equals 3. These are the local maximum and minimums. The word absolute has a synonym. Global extrema is the one value which is bigger than all others. It's the one value that is bigger or smaller than all others. So the absolute maximum of this graph is going to be 2. That's because here at this point where it reaches its absolute highest, the y value is 2. This occurs at x equals to 3. The absolute minimum of this is going to be -3, because this occurs here at x equals -4. Example 2. Discuss with the person next to you, have a go at this question, see if you can write down the answers, then we'll run through them in a
Wait,
second.
sorry, can we go back for a second? I missed something.
So our first one is, what are the relative minimum? So our relative minimum is going to be here at this point, and that is going to be at x equals minus 2.
What's the difference between local and relative?
Synonyms.
Same thing.
Yeah.
So
There's two words, absolute and global, the same, relative and local.
So how come last time we put like we put several points?
There was that. Last time it's one.
Oh, there's only one.
Yeah.
But then there's gonna be two maximum for
Yes.
Okay.
Relative maximum, we're going to have minus 4 and 3.
Yeah. Because see how it doesn't go down? It just stays the same.
Maximum, it's the greatest of all maximums, right?
Yeah.
So when we come to relative maximum, we also include the maximum.
Yeah.
Is minus 3 a maximum?
Absolute although on that one, some teachers or some textbooks will vary slightly and not include endpoints, but they should be.
So endpoints also count.
Yeah.
What about that arrow down there with arrow 5?
We'll talk about. Okay, so the absolute minimum of this one,
Is it none?
none. Why is it none?
Because there's an arrow going down to negative.
Yeah. So this will just keep going lower and lower. It's an endless, it's just going to approach infinity, negative infinity. It's just going to keep getting smaller and smaller. You can't actually specify any particular value on this one, so there is none available. So the best way to write it would be does not exist, DNE. Absolute minimum does not exist. Infinity doesn't exist. There's always a number after it. Okay, absolute maximum. So the absolute maximum is going to be 2, and this occurs at x equals 3. Here in the second one, our relative minimum.
Negative 3, 3.
We have negative 3 and 3. Relative maximum.
0.
Oh, 0.
Negative 4,
Yeah, 0.
0, 5. Absolute minimum.
Negative 3.
Where does this occur?
My x is negative 3.
Absolute maximum.
4.
5.
Sorry, don't shout
Oh,
out.
sorry.
Don't shout out. Let's have somebody else involved. Haven't heard anything from the table over here. Let's hear you guys.
3 and 6.
What is the absolute maximum going to be?
Oh, maximum.
Is that a
No.
Maximum mean
What's the absolute maximum going to be?
how many is it?
So the absolute maximum is going to be 4. This occurs at x equals 5. Discuss with the person next to you these true or false questions. Okay, true or false? Between two real zeros of a polynomial, there must be at least one minimum or local minimum or local maximum. Is this true or false? This is going to be true. This is going to be true. If you've got two zeros, well, firstly, it tells us that it's a polynomial function. So with it being a polynomial function, it means it's got to sort of wiggle up and down like this. It can't do anything crazy like a rational function would. This wouldn't be true for a rational function. It's got to go whizzing off. It's got to go up and down like this. So if you have at any point any roots, in order to go from 0 through 0 back to 0 again, you've got to turn around and come back down again. So between any two real zeros of a polynomial, there must be at least one local maximum or one local minimum. Question 2. A polynomial of nth degree must have n minus 1 turning points.
False.
How? Why is it false?
Because it's not the degree of the polynomial that matters.
Why?
I'm not sure.
So Proof is really hard to do. To prove things is quite difficult. To disprove them is very easy. You find one counter example. Find me a counter example that would disprove this one or show this one to be false. Think of a function that you know of. Yeah, perfect. So, for instance, x to the power of 4 is a 4th degree polynomial. Y equals x to the 4. Looks like this. It's going to have one turning point, not n minus 1.
Sorry? Can I have n minus 1 or less turning points?
Yes, that would be correct. It will have n minus 1 or less. It can't have n or more, definitely. So for instance, you're familiar with this. A linear function, 1st degree, has no turning points. A quadratic function, 2nd degree, it has 1 turning point. A cubic one could have 3 or 1. A cubic function can have 3 or 1. Sorry, no, a cubic one can have 2 or none. Sorry, 2 or none. It's 1 up. Okay, so number 3, a polynomial of even degree must have either a global minimum or a global maximum.
False.
What do we think here on this one?
True.
True?
False. False.
So even degree. Quadratic, we know how that one looks. They always have a turning point. 4th degree, it's going to have at least 1 turning point. So this one is true. So if it's even degree, it's going to have at least one local extreme. It's going to have at least 1. A polynomial of odd degree can have neither a global minimum nor a global maximum.
True. Neither. Oh, yeah, that's true. Yeah, true. It's true. It's true.
Yeah, this one's true. Because unless it has a restricted domain. So this type of a function, a good example would be something like this one. Is it's going to continue without bound towards infinity and towards negative infinity. Unless it has a restricted domain. There's no mention of a restricted domain on this one.
Who said it's true?
So I would say this is true, and I would quantify that there is no restricted domain. 5. Points of inflection of a polynomial function occur at input values where the rate of change of the function changes from increasing to decreasing, or from decreasing to increasing. Now this one's key. This one's key for us. We've done this one so far. What do we think?
True.
This one is true. So you are changing from concave up to concave down at a point of inflection. And at the point of inflection, when it is concave up, the rate of change is increasing. At a point of inflection, when there is concave down, the rate of change is decreasing. So for it to change from increasing to decreasing is because we are at a point of inflection, and it's changing concavity at this point. So points of inflection occur when a function changes from concave up to concave down, or from concave down to concave up. When it changes, that means the rate of which the function, the rate of change is changing from increasing to decreasing, or vice versa. At a point of inflection, the rate of change of a function changes from increasing or decreasing, or vice versa. I knew that was a good thing to say after that first sentence. Example 3. The graph shows as a figure. We can use G to answer the following question. Find any value of x where G has a point of inflection. Can we see a point of inflection? How many points of inflection can we see? Let's say hands in the air. Let's have hands in the air. 0, 1, 2, 3, 4. Can we see hands in the air on this one? Votes.
Wait. Yeah.
Is that a 0 on yours?
Oh, I'm sure.
Okay. we are going to get 2, obviously. We have 2 changes in concavity. Where does it change concavity? It's going to be concave up here. That's concave up. It's going to be concave up here. It's going to be concave down here. These are concave down. So it has 2 points of reflection. This is going to occur at x equals minus 1 and x equals 1. For each of the following intervals, determine if the rate of change is increasing or decreasing. Explain the reasoning for your choice. So from 3 to 4, where are we at 3 to 4? So we are here. From 3 to 4. Is the rate of change increasing or decreasing?
Increasing.
It's increasing. Why?
Because it's concave up.
Perfect. Concave up. So it is increasing. Let's start with the reason. Concave up, which implies rate of change increasing. Okay, have a go at doing the other 3 for yourselves. Let's have a look at our answers. So number 2, what have we got here? Number 2, we're looking at which interval? Minus 4 to, we're looking here. So what do we have here? Is it concave up or down? Up. This is concave up. This implies the rate of change is increasing. Interval 3. Where is interval 3? Negative 1 to 1.
Concave down.
Concave down. What does that imply?
Decreasing.
No.
It's negative.
Concave down, what does that imply?
Increasing.
No.
The rate of change is decreasing.
Rate of change is decreasing. You've got to be really careful because you can't just say increasing, decreasing, because the function could be increasing. Here, the function's decreasing, the rate of change is increasing. Here, the rate of change is increasing, and so is the function. Here, the rate of change is decreasing, the function is doing both. The average rate of change is 0. So, the rate of change is decreasing. You have to be clear about which of the 2 elements that you're describing. So then from 1 to 2, let me just section it off there, that's it. 1, this one is concave up. If it's concave up, what does that imply?
Rate of change increasing.
The rate of change is increasing. Okay, take out your calculators. We're going to do a calculator question. Have a go at this one.
I've seen this one.
Yes.
So hot.
Okay, so we should have our calculator ready. We're using the TI Inspire. The recommended calculator for this class here at the school is TI Inspire CX2-T. You can see it here in the video. This is the calculator we recommend most for students. This is the more affordable option. When using the calculator, follow me along with your calculator in your hand if you need some instruction on how to use it. What I recommend is always pressing on when you start and creating a new document, not using the scratch pad. We're making a document here and then saying no to the previous one and we don't save it. Always add a calculator page. You always come back and have to do calculations. This question is a modeling question, so we're going to need to enter the function. So we press the control button here on the left. You can see it lighting up on my video where I'm pressing. And then here you can press add page, which is above documents, and it lets us add a graph page. Most of the menus have numbers on them, so instead of using the touchpad here to scroll up and down, it's quicker just pressing the numbers on your keypad, and you go a lot quicker. And then we have to enter in the function as shown here. What I recommend, we have two negative symbols on this calculator. This one in black on the keyboard is to do with numbers. This is the negative. This is the negative. This one in white on the right, that one is subtract. That's the operation of subtraction. They are different. So this is the unitary negative, and the other one is the subtraction. So in this case, at the beginning, we want a negative number. So we use the black one here. We want the negative, 1.37. And then we have to do a variable substitution. So this the function c in the question is given over the domain of time. But in order for us to graph it, we will graph c of x. So this means we do a substitution of all our t's for x, and then we're going to raise it to the power of 5, scroll to the right. We can do the next bit, we're going to do plus 4.218 x, and then cubed. Now we have a subtraction. So this is a subtraction symbol. We use the white one over here, we do subtraction. You can see ever so slightly, they look different on the screen. The subtraction is slightly longer, the negative is slightly higher. You can subtly notice the difference.
It's not 3, it should be 4.
Ooh, thank you, I see that. And then we've got 0.357x squared plus 3. So we type the function in like this. Type the function, press enter, it will draw it in the standard window. What's the question going to ask us to do? So from 0 to 3. So we're only interested in the interval from 0 to 3. So let's restrict the domain. The best way to do is use your touchpad here, like this, and scroll your mouse down to these numbers. If you click on them, you can just change them. So we want that one to be 0, and then we press enter. And then let's click on this one. We can change this one to 3. Now we've restricted the domain, we need to be able to see the function in this interval. So we're going to have to extend our x and y values. So let's make the y value, we can make this one a little bit shorter. Just going to make it -1. I always have a little bit below the x-axis. I just like the way it looks on my screen for me. I can clearly see I could start it at 0, but I want to see the axis as well. So I like to do it that way. Let's extend this one up a little bit, see when we can see something. So I'll just try 20 to begin with. I can see I'm getting a bit of a maximum up there. Let's go a little bit higher. Let's try about 50 for that one. And I can see the necessary information here on the function. All right, so based on the model, at what time t does the number of cars in the parking lot change from increasing to decreasing? So if we're looking at this graph, the graph is modeling the number of cars in the parking lot. So C of t is the number of cars in the parking lot. So it reaches a maximum. Let's find the maximum here using the calculator. We press menu, analyze graph. We want a maximum. And then you have to give in 2 bounds. So use the touchpad here for this one. You have to slide it to a point where your lower bound is to the left of where it occurs, and then you click in the center. Watch for the word bound, changing from lower bound to upper bound. And then we scroll over to the other side and press tab, the center again. This will locate the maximum point for us. Now, is there a point of inflection?
Yeah.
Somewhere around here there's a point of inflection. So if we analyze the graph, no, let's not do that. Okay.
2.39. I just selected the maximum.
Okay.
Wait, what?
I was going to do a bit of a side quest there, but I'm not going to. So based on this model, at what time do the number of cars in the parking lot change from increasing to decreasing? So do we want when the rate of change changes from increasing to decreasing, or do we want when the function changes from increasing to decreasing?
Function.
So you have to read carefully the wording on this one, and it's the function. We want when the function changes from increasing to decreasing. Where does it do that? At the vertex, at the maximum. So the function will change from increasing to decreasing at the maximum. The rate of change changes from increasing to decreasing at the point of inflection. So this one we are going to want one of these two numbers. Which of the two numbers do we want?
2.45.
2.45. 2.45.
What's the question saying? Based on the model, at what time? So it's the t value, in this case the x value. Now 2.45 is not enough for this. 2.45 is not enough. This, why not? Not quite.
It's not time.
It is.
We need minute.
Hours?
Yeah, hours.
Yeah? No.
It's, you put in seconds maybe?
No.
Do you have to convert 2.45
No.
to other units?
No.
You enjoy
What's the question? Is it an exact value? It's rounded. What must we give all our approximations to?
3 decimal.
How many decimal places do we have here?
2.
So with the calculator, press document, settings, document settings, and change from float 3 to fix 3. Fix 3 is the setting that we want. But if you notice, it doesn't change here. It will change here. Look, I've changed it on this page. Oops. I've changed it here on this page. To 3 decimal places, but for some reason, the graphing page has a separate setting. It's not in this one here with the document settings, that is the general settings. But for some reason, there are some extra settings for the graphing page and the geometry pages. So this is the graphing page. So here on the settings, we have graph and geometry settings. These ones have their own separate settings. So on this one, instead of being in float 3, you would want to move to fix 3. Now we have 3 decimal places. I would recommend having those 2 settings for this set left of this course, because everything when it comes to a decimal approximation can be to 3, should be to 3 decimal places. So leave them on fixed 3. So we have the answer. T is 2.446 hours.
20 minutes.
Now, you're right. 3 decimal places for this number is stupid. We don't need that. 1 decimal place is enough. It's approximately after 2.5 hours. That is a sensible number. When it comes down to that 6,000ths of an hour, that is not a sensible number for the setting situation. But this course doesn't think like that. It requires that you give all approximations to 3 decimal places, regardless of how irrelevant that information is. Last question. No calculator for this one. Have a go at this question.
No, sir. Could I put in charge now?
So this one is, we're going to be looking at the roots. What are the roots of this function? What are the roots to begin with? Where do the roots occur?
-2.
So this factor here gives us x equals -2. What's the multiplicity of that?
1.
1. This one has a multiplicity. Multiplicity of 1. We have another one here. This is x is equal to what? What's the root here?
2. Oh, I mean, 4.
This is x is equal to 4. What's the multiplicity?
2.
The multiplicity is 2. And this last one?
0.
This is going to give us x is equal to 0. The multiplicity here is equal to 1. how do we know how it looks? So what we basically know at this point is where the roots occur. Let me sketch it here. So we are going to have a root at -2. We're going to have one at 0, and we are going to have one at 4. So the graph is going to get to 0 at these points. Now, there are 3 ways it can have a root. There are 3 possibilities, and it links to the multiplicity. So this, let me just put up some examples. So we can get a 0 that looks like this. We can get a 0 that looks like this. And this is when the multiplicity equals 1. We can get what we sometimes call a bounce. This means the turning point is also the root. So when the turning point is also the root, we are going to get one of these, like a bounce. This is when the multiplicity is even. Our third one is we're going to get a point of inflection as the root. And this is when we are odd and greater than 1. So these are the 3 possibilities. Based on the multiplicity, the root is either going to be a straight line, a turning point, or a point of inflection. If it's 1, if it's even, or if it's 3 or higher, an odd. So here at -2, we are going to be going through as a straight line. Here at this point, we are going to be having a bounce. Here at this point, here at this point we're going straight through, and here at this point we're going to have a bounce. Now, there's 2 possible graphs to this. We haven't covered, we're going to cover next class as to which one it will be. But let's say we start at -infinity and we go through once, and then we go through once. In order for us to do a bounce here like this one, we've got to turn around and come back to it like this, and then go down like that. The other alternative is that we start it off up here. If we start off up here, we're going to go like that, and then we're going to have our bounce and go up like this. To tell whether it's the red or the blue, it's easy. You look at the lead coefficient. If the lead coefficient is positive, it's the red. If the lead coefficient is negative, it's the blue. We can see here that the lead coefficient is going to be +1. You expand that bracket, it's going to give you 1x to the power of 4. It's the lead term. You don't have to expand the whole term. You just take the first one in each one and multiply them together, and you see what the lead term is. You can also see the last term is going to be -8. The middle terms will take a lot longer to work out. The middle terms will take a lot longer, but the first term and the constant, the lead coefficient and the constant term is very easy to see. So this one is going to be this red one. How many turning points does this function have now? 3. I've got a great exam tip for you now. I put a box around my answer there so it stands out on the page. Listen to my exam tip. Don't ever do this. Don't ever do this on an AP exam. The examiners are instructed that if an answer is highlighted, then to mark that one whether it's correct or not. If there is no answer highlighted like this and there's a solution, they will look through the solution to see if there's an answer there. So if your work is a little bit, you've got maybe a right answer and a wrong answer, typically what happens is you might come to the correct answer, and then you might simplify it one step further and make it wrong. You get the idea. You've got some algebra, you're doing your algebra, you get to the answer, and then you simplify it to the next answer. Let's say the answer is 50/2, and then you simplify this to 26. If you put a box around the 26, you're getting it wrong. If you don't put a box around the 6, they will mark the 50/2 correct, because maybe that was all the work necessary to get to that point. Okay? So my exam tip for you is don't put a box around your answer. leave it to the examiner to determine which of your answers they're going to assess. And this might get you an extra point. All right, that is it for today.